At this point, we've completed the first major topic in physics, kinematics, which describes how things move. We are now ready to move on to the next chapter, forces, which explains why things move. If you had to explain to a 5-year-old what a force is, you might generically say it is a push or a pull. And you'd be right. Whenever one object pushes or pulls on another, we say it's exerting a force on it. This already establishes one characteristic of forces. Two objects must be involved, one to exert the force and the other to feel it. Here, we see a character exerting a force on a heavy object and pulling it leftward. A second important characteristic implied by push or pull is that forces have directions. They are vectors. Now, let's take a look at what a force does. The simplest way to envision forces is to visualize them in space. Here is an astronaut throwing a football that is initially at rest. We see the astronaut push it. We could say the astronaut is applying a force, and as the object is pushed, it picks up speed. It accelerates. But now notice something. Eventually, the object loses contact with the astronaut's hand. From this point onward, the astronaut is not applying a force anymore, and yet the object doesn't stop moving. It keeps traveling, even though there's nothing pushing on it anymore. You might ask about gravity, but the object is so far away from any planet or star that gravity is negligible. It just keeps moving. This reveals something profound about forces. I want to highlight it because there is a common misconception at play and we must move past it right now. Forces do not make objects move. They make objects accelerate. An object can move perfectly fine without experiencing a force. It just can't accelerate. In this example, the push from the astronaut was needed to start the object moving, to give it velocity, to accelerate it from rest. But once the object was moving, the astronaut did not need to push further to keep the object moving. The object will keep moving forever, even in the absence of a force. You don't need a force to make something move. You need a force to make something accelerate. Now, let's revisit the definition of acceleration. Acceleration is a change in velocity. Since velocity is a vector, that means a change in either the size of the velocity or the direction of the velocity. In a nutshell, acceleration means an object is speeding up, slowing down, or changing direction. And since forces cause acceleration, we can say forces cause objects to speed up, slow down, or change direction. Without force, an object cannot accelerate. It cannot change velocity. If its initial velocity was 0, that is, if it was at rest, it must stay at rest. If it were moving at a certain speed in a certain direction, it must continue to move at that speed in that direction. In fact, it will move in a straight line at constant speed forever. Here is a rather unfortunate example of that last point. When our protagonist skateboards onto the ramp, the skateboard sticks to the ramp. The ramp exerts a force on the skateboard to make it stop. That is, the skateboard is accelerated, it slows down. But the skateboarder was unrestrained. He felt no such force to change his velocity. So he keeps moving and flies off the skateboard. Without the force of something to slow him down, he will keep moving at a straight line at constant velocity in accordance with Newton's first law. One last caveat. So far, we've examined one force acting on an object, but you can have multiple forces acting. What if there are two equal forces and they act in opposite directions? Here, for example, we see a rope being pulled equally from both sides, but it isn't moving. Why? Because forces are vectors. Equal pulls that point in opposite directions will cancel each other out. So there's no overall force and therefore no acceleration. We can take all the characteristics we have about forces and summarize them into one statement. Unbalanced forces cause acceleration. This is Newton's first law of motion, and there's a lot that's packed into that one statement. If an object feels no force, it cannot accelerate. If it is at rest, it will stay at rest. And if it's moving, it will continue moving in a straight line at constant speed. Force is not required for motion. Force is only required for acceleration. And when we say acceleration, we mean speeding up, slowing down, or changing direction. If two forces point in opposite directions, they can cancel each other out. If they do, the total force on the object is zero, and there is no acceleration possible. And we can express this statement even more simply, as an equation. The total force that something feels is related to its acceleration. It turns out that the proportionality constant is the mass of the object. This is the first time we've ever seen the mass of an object be relevant to any calculation. What this equation says is the greater the mass of an object, the harder it is to accelerate, the more force is required to accelerate it. This equation is known as Newton's second law. We will use this as a central relationship in every puzzle we see from this point onward. But for the moment, we'll just look at a few more basics of how forces work. We mentioned before that forces are vectors. They have a size or a strength and direction. How do we evaluate the strength of a force? We get some clue from the structure of Newton's second. Force equals mass times acceleration. Mass is measured in kilograms, and acceleration is measured in meters per second squared. So the units of force must be the product of those individual units. But it gets a little awkward saying kilogram meters per second squared over and over. Instead, we call the unit the Newton. Force is measured in newtons. 1 Newton is the amount of force that is needed to accelerate a 1 kilogram object at 1 meter per second squared. To put this in day-to-day terms, to lift an apple, you need to apply about 1 Newton of force. To open a sliding screen door, you might need to apply about 10 newtons of force. To lift a 10-pound dumbbell, you need about 50 newtons of force, and so forth. Now consider this situation. This character stands at rest on a skateboard, and he throws the ball. He's pushing the ball, which means he's applying a force on it to accelerate it. But as he does this, he starts recoiling, he starts traveling backward. Now, since he was initially at rest and then started moving, he experienced a change in velocity, which means he accelerated, which means a force must have acted on him. But where did this force come from? The answer is from the ball. At the same time that he was applying a force on the ball to push it leftward, it was applying a force on him, pushing him rightward. Newton's third law says if you exert a force on an object, it exerts an equal and opposite force on you. But if the forces are equal, why doesn't he move with the same acceleration as the ball? Newton's second law tells us that force is related to acceleration through mass. The same force applied to a heavy object must produce a small acceleration, and that's what we see. The ball is light, so the same force produces a large acceleration. But the character has a much greater mass, so the same force produces a smaller acceleration on him. At this point, you might be wondering, if our character exerted a force on the ball, and the ball exerted an equal and opposite force on the character, why don't those two forces cancel, just like what we saw with the tug-of-war earlier? The answer is, for two forces to cancel, they must be on the same object. Here we see two skaters. If they push on the ground to do a kickflip with the same 20 newtons of force, the two forces might be equal, and they might be pointed in opposite directions, but they wouldn't cancel because they're not on the same object. Likewise, when our character throws the ball, the force is on the ball, but his recoil is because of a force on him. One force is on the ball, the other force is on the man. The forces are on two different objects, and therefore they do not cancel. This video introduced the concept of forces and introduced Newton's laws, the rules of how forces operate. In the next video, we will explore how to use these laws, particularly the second law, to explain the motions of objects.